Welcome, business calculus students. This is Mrs. Shannon Cornell. I'm going to be working through your midterm review in a series of videos. I'm going to be working through these problems pretty quickly, so feel free to pause and reverse and watch over and over until you fully understand the concept. In this video, I'm going to be working problems 1 through 8 from your midterm review. Remember, you can print this from Blackboard and you can have it in front of you and work through it with me together. Starting with problem number 1, we're going to be looking at manipulating limits. So in problem number 1, we're given two limits. The limit as x approaches 9 of f of x equals 11, and the limit as x approaches 9 of g of x equals 6. Now we don't know the functions f of x and g of x, so we can't evaluate these directly. We're going to have to use rules of limits to do so. So the problem says use limit rules to find the limit as x approaches 9 of the difference of the two functions, f of x minus g of x. This is really a simple problem involving substitution. So to evaluate the limit as x approaches 9 of f of x minus g of x, we're going to find the limit of each individual function and then calculate their difference. So we can expand this as the limit as x approaches 9 of f of x minus the limit as x approaches 9 of g of x. Using the given limit values stated in problem 1, we can use substitution to evaluate. The limit as x approaches 9 of f of x, this entire expression is going to be replaced with the value of the limit, which is 11. Then we're going to subtract the value of the limit as x approaches 9 of g of x, which is given to be 6. So all we have to do here is evaluate 11 minus 6, and we've calculated our new limit. So no problem. We just have to recognize we're replacing those limit expressions with their values. Let's try problem number 2. Again, we're given two limits. This time x is approaching 5. Notice that x is approaching 5 in both limits. If we didn't have the same target value, we wouldn't be able to combine the limits like this. This time we're finding the limit as x approaches 5 of the quotient of f of x and g of x. So using rules of limits, we can find the limit as x approaches 5 of the top function and the limit as x approaches 5 of the bottom function. Now, please remember, this is a very convenient rule, but it only works with limits. That is, you can take that limit operator and apply it to both the numerator and the denominator individually. Remember, this does not work with derivatives. Right? To find the derivative of a quotient, we have to use that fancy quotient rule. We can't just differentiate the top and the bottom, so be very careful about that. Limits are special in this. So back to the problem. We first need to evaluate the limit as x approaches 5 of f of x. This entire expression in the numerator is going to be replaced by its given value, which is 8. And in the denominator, we have the limit as x approaches 5 of g of x. We're going to replace that entire expression that we see there in the denominator with its value given to be 32. All we lack here is to reduce this fraction, and of course, 8 over 32 reduces to 1/4. So again, we don't know f and g, but by applying rules of limits, we're able to evaluate the combined limit. One more problem here. Limit to x approaching 4 of f of x is 64. Use limit rules to find the limit as x approaches 4 of the square root of f of x. In your studies, you came across a rule that allows you to move this outside operation, the radical, over the entire limit. So what we're going to do is transfer this limit operator to the meat of this problem. And the meat of that problem is that function f of x. And switch it with the outside operation there, which is the square root. So the limit as x approaches 4 of the square root of f of x is the same thing as finding the square root of the limit as x approaches 4 of f of x. It's simply a matter of order of operations. Now I can evaluate this limit in the radicand because that was the given information, right? So I can replace that with its value, which is 64. And I still have that outside radical to deal with. And of course, the square root of 64 is 8. So those are several problems allowing you to practice using the rules of limits. Make sure that you study all of the rules to be prepared for your midterm exam. Next, we're going to be dealing with actual functions. Instead of given unknown function names like f and g, we're going to have function rules to deal with. So the next series of problems says use properties of limits to find the indicated limit. It may be necessary to rewrite the expression before limit properties can be applied. So on problem 4, we have the limit as x approaches 3 of this big rational function. Your first attempt in evaluating a limit should always be direct substitution. Now I notice if I take this target value, 3, and I plug it in for x, I'm just looking at the denominator here, I would obtain a 0 in the denominator because 3 squared is 9 and 9 minus 9 is 0. Since we get a 0 in the denominator, we are unable to evaluate this limit by direct substitution. So we're going to have to do some sneaky algebra to sort of outsmart that denominator. So if you cannot evaluate the limit by direct substitution, attempt to factor your rational expression and see if you can cancel anything. So let's do just that. We're going to carry our limit operator all the way through the problem until we've actually evaluated the limit. So the numerator, x squared plus 6x minus 27, factors easily as x plus 9, x minus 3. And the denominator, which is the difference of two squares, factors as x plus 3 times x minus 3. Now, in factoring, notice we have a common factor between the numerator and the denominator. That means we're going to be able to reduce that fraction. Observe, we are removing the factor that's causing the problem, right? If I plug x equals 3 into this factor, that's where I'm getting the 0 in the denominator. However, after we factored and canceled, that problem is no longer there. Here's what remains. The limit as x approaches 3 of x plus 9 over x plus 3. In this reduced form, we are now able to evaluate by direct substitution. That means I can take this target value, I can plug it in for x, and I don't obtain a 0 in the denominator. Thus, I will have calculated the value of the limit. Notice when we're actually calculating the limit, we then drop that limit operator, which is sort of a pending operation all along. We have 3 plus 9 over 3 plus 3. 3 plus 9 is 12 in the numerator. 3 plus 3 is 6. When we reduce that fraction, we obtain the correct value of the limit, which is 2. So on that problem, again, we could not evaluate by direct substitution because we obtained a 0 in the denominator. So we got around that problem by factoring both the numerator and denominator. We canceled out the trouble factor. Then we were able to evaluate the limit by direct substitution. Remember that technique on your midterm exam. Problem number 5 has a similar issue. If I try to plug in my target value, 49, specifically in the denominator, I would obtain 49 minus 49, which is 0 in the denominator. And we know we cannot have a 0 in the denominator. So on this problem, we're not going to factor it like we did problem number 4. We're going to use the technique of rationalization. You can rationalize either the numerator or the denominator depending on where your radical is. In this problem, the radical is in the numerator. So what I'm going to do is carry my limit operator until I'm ready to actually evaluate, but I'm going to rationalize the numerator. So here's the original problem. I'm going to multiply the top and the bottom by the conjugate of that numerator. So I've got the same two terms, but different signs in between. Whenever I add those parentheses to the top and the bottom in all the appropriate places, it signals to my brain I should FOIL. Now be really careful here. What I want to do is FOIL only the top and leave the denominator factored. You'll see why here in a minute. When we FOIL the numerator, we multiply the first two terms together. That is square root of x times square root of x. That gives me x. When we multiply the outside terms together, we get plus 7 square root of x. And when we multiply the inside terms together, notice we get minus 7 square root of x. Those are going to cancel out, and that will happen every time when you apply the conjugate. Now, multiplying our last two terms together, we have negative 7 times positive 7. That gives me minus 49. Now, do you see why we want to hold off on FOILing out the denominator? I can see the factor x minus 49 now lives in the numerator and the denominator. So by leaving it in this factored form, I'm able to cancel out that trouble factor, the one that was causing the 0 in the denominator, and now my reduced fraction, I can evaluate the limit by direct substitution. So let's do just that. Remember, when we are ready to evaluate the limit, we drop the limit operator, we plug in our target value, and calculate. In the denominator, we have 1 over the square root of 49 plus 7. That's 1 over 7 plus 7, which reduces to 1 over 14. So on both of those problems, remember those two techniques. If you cannot evaluate the limit by direct substitution, that means when you plug in your target value and you get a 0 in the denominator, you have two algebraic techniques to try. You can factor and cancel, as we did on problem 4, then evaluate by direct substitution. Or if your function contains a radical, you can rationalize either the numerator or the denominator, depending on where that radical appears, cancel the trouble factor, and then evaluate the limit by direct substitution. So again, practice those problems. Expect some like that on your midterm. The next series of problems deal with limits at infinity. So we're going to use different techniques to evaluate limits at infinity. Now, you can do it the long way, or you can memorize 3 shortcut rules to evaluate these very quickly. And I'll show you both ways. The way to calculate a limit at infinity every single time that will work is to divide every term in the numerator and the denominator by the highest power of x in the denominator. So notice in this case, the highest power of x in the denominator is x to the power of 1. So I'm going to divide every term in this limit by x. By dividing each term by the same thing, I'm not changing the original function. Next step, we can reduce. 8x divided by x reduces to give us just an 8 in the numerator. 5x divided by x reduces to give us 5, and 3 over x is completely simplified. Applying rules of limits, we can find the limit of each term individually. So we have the limit as x approaches infinity of the term in the top, divided by the limit as x approaches infinity of 5, minus the limit as x approaches infinity of 3 over x. Now, we know that the limit of a constant is a constant. So the limit as x approaches infinity of both 8 and 5 is the 8 and the 5. But on the last term in the denominator, we have the limit as x approaches infinity of 3 over x. As this denominator grows without bounds, the value of the fraction crashes down to 0. So as the denominator grows without bounds, the value of the fraction crashes to 0. This leaves us with 8 over 5 minus 0, which simplifies to 8 over 5. So the value of that limit is 8 over 5. On this problem, notice that the degree of the numerator and the denominator were equal. When this happens, here's a great shortcut. If the degree of the numerator is equal to the degree of the denominator, then the limit is the ratio of leading coefficients. If you can remember that, you can sort of shortcut this problem. So again, the degree, or the highest power of x that I can find in both the numerator and the denominator, is 1, so they have equal degrees. Therefore, the limit is the ratio of leading coefficients. And notice that's exactly what we obtained for our answer. Remember that here in a minute when we get to problem 8. Number 7, we have another limit at infinity. So we're going to use this same technique of dividing all of the terms in the fraction by the highest power of x from the denominator. So notice the highest power of x in this case, and the denominator is 4. So let me scoot over here so I have plenty of room to work. I'm going to divide each term by x to the 4th. Then I'm going to go back and reduce each one of those fractions. So I'm going to run out of room here. I'll move it down here. 2x cubed divided by x to the 4th. Looks like we're going to have an x remaining in the denominator here. On the next two terms, missed an x there, didn't I? Better make sure and include that. When I reduce, I end up with 9 over x to the 3rd power. The last term is already reduced. That takes care of the numerator. In the denominator, when we reduce, we have a 4 for our first term. In the second term, this leaves behind 9 over x cubed, and we cannot reduce that last fraction. Okay, now if we go back and evaluate the limit as x approaches infinity of each term, remember, if we have a constant in the numerator and an x growing without bounds in the denominator, that's going to cause the fraction to crash down to 0. So all of these fractions are going to head to 0, except for that constant 4 in the denominator. Evaluating this limit, we come up with 0 over 4, or 0. So the value of this limit, I'll sneak it in here in the answer blank, is 0. Now, another shortcut. Notice in the original problem that the highest degree of the numerator is less than the highest degree in the denominator. When this occurs, the limit is automatically 0. So let's review those two shortcuts. If the degrees are equal, the limit is the ratio of leading coefficients. If the degree of the top is less than the degree of the bottom, then the limit is 0. So those shortcuts are a great way to check the work that you have shown. Let's work one more problem from this video, which involves limits. Problem number 8, and then we will conclude the first video in the midterm review series. It says the population of a culture of tumor cells is given by P of t equals 3,300 times t divided by quantity t plus 3, where t is time in days. Calculate the limit as t approaches infinity of P of t. So notice t is time in days, and P of t is population. So what we're saying here, as time changes, how does the population of cells change? That means how is this tumor growing or decreasing by measuring the number of cells? When we calculate the limit as t approaches infinity, notice in our function, the degree of the top is equal to the degree of the bottom. That means the highest power of t that I can find in the numerator and denominator is the same. So if we use our shortcut, we know that the limit will end up being the ratio of leading coefficients. So the limit of this function is 3,300. Okay, just by taking the ratio of leading coefficients. If you forget that shortcut, remember you can go through and divide each term by t. You'll come up with the same conclusion. Now, interpret the meaning of the limit in a complete sentence. So we're just going to talk about what both variables are doing. First of all, t, time in days, is approaching infinity. That simply means that time is ticking on and on and on. So we're looking at the population in the long run. So we could say as time increases indefinitely, that's what the t variable is doing. Let's look at what the p variable does. P represents the number of cells in the tumor. So as time increases indefinitely, our limit is 3,300 cells. We could say the number of cells in the tumor settles at 3,300 cells. Okay, so that simply indicates that the tumor is not going to grow beyond that point. It's going to reach that steady state time where the number of cells remains at 3,300. All right, so that concludes the limit section of your midterm review. Again, feel free to go back through these problems if you need to hear it again and practice again. If you feel comfortable with these problems, you will feel comfortable on that midterm exam. So practice, practice, print it out, work it a couple more times if you need to. Use this to prepare for that midterm exam. In the next video, we will talk about continuity.